I'm really happy to be here. It's my first time to be here, and I never made it to this campus, but it's really nice. I'm impressed. It's inspiring. It reminds me a little bit to I don't know, Stanford or Berkeley or something like that. So it's really nice to be here. And and thank you very much also for sharing the next 60, or depending on how long question and answer will be, 90 minutes maybe with me. And so my talk is about 15 years of carbonate-based ionic liquid synthesis. That's our proprietary way to produce ionic liquids. And that's the reason why I founded the company, because I invented a new process to synthesize ionic liquids on an industrial scale. The background title, or the second title, is the startup journey from a Greek beach. You will see why, from a Greek beach to world leadership in manufacture of ionic liquids. Or let's better say two words, world leadership. I don't know if we are already world leadership, but we are close to it. And so I just want to also let you know about how the whole story started, how simple it started really in a garage and what it is now. So I'm gonna introduce ionic liquids to you because I think probably some of you are not familiar with ionic liquids. So actually it comes into my mind. I have two samples in my car. I forgot to take them with me, I'm sorry. But it's not much to see, it's just a viscous liquid, but it's a lot what it's inside this liquid. I'm gonna tell you the story of proionic and the Civils technology. I think you should know something about the really fascinating properties of ionic liquids, because they are really something different. They have properties which are not available in other classes of liquids. And then this is something like a flashlight. I will give you a flavor of how you can apply these ionic liquids actually and implement them in technology, but also in medical applications and other applications. You will see there are hundreds of fields where you can apply ionic liquids. Just to give you a flavor, what probably could be useful for your field you are working in. So I start with ionic liquids. What are ionic liquids? You all know ionic solids like sodium chloride. So an ionic solid like sodium chloride has a very regular lattice of sphere-shaped cations and anions with a high order in the long distance and in the short distance. And there is the Coulomb force between those ions, and the Coulomb force is a very strong force. And so you need a lot of heat in order to melt such a sodium chloride crystal, something like 800 degrees C. And if you melt sodium chloride, you end up with a liquid which consists entirely out of ions, but you cannot really use it for a lot because it's too hot. So you cannot do a lot of things with molten sodium chloride. We have a completely different picture if we combine organic cations and inorganic or organic anions the right way. We can produce salts with a very low melting point, per definition below 100 degrees centigrade, but sometimes even much lower, down to even -60, for example. And if you have such an ionic liquid in its liquid state, you have a completely different thing than a molten inorganic salt, because this liquid seems to be just a liquid, but if you beam an X-ray through it, you will see on the other side, you will get a pattern. So there must be a structure inside this liquid. The same thing happens if you make a neutron beam experiment, for example, you will get a pattern. So it turns out that these liquids are structured. They are segregated, what we call it, into domains, and these domains can be polar, they can be apolar, and they can even be fluorophilic. And these domains, some 20 years ago, when I started with ionic liquids, were more theory. Nowadays, there are several experiments which prove the existence of these domains, including spectroscopic methods, but also direct proofs, like using an ionic liquid as a template, for example. You can make macroporous silicon dioxide aerogels with a completely equal pore distribution, because the monomer, where you start making it from, penetrates into those domains, and those domains are very regular. They have very regular dimensions, and you can polymerize, and then you can calcinate it, and then what's left is the silicon dioxide backbone, and this proves to be a direct proof for the existence of those cavities inside ionic liquids. So depending on the length of the alkyl chain, those structures go from globular to sponge-like, but they really exist, and they contribute some to some theories why ionic liquids behave like they are. I'm not going to make too much chemistry, so I would like to stay a little bit more and look on it from a higher altitude to the whole field. I know not everybody here in the room is chemists, so I'm not going to bore you with chemistry, but we need some chemistry, of course. And these are some typical cations for ionic liquids. We have the prominent imidazolium cations, pyridinium cations, piperidinium, morpholinium, pyrrolidinium, ammonium, quaternary ammonium, phosphonium, can even be natural occurring ions like this collinium, for example. And all those R's, of course, are substituents, which can be diverse. And you can combine these cations with even more anions, simple inorganic anions, complex inorganic anions, fluorocations like triflate, for example, or bistriflamide, amino acids, fatty acid anions, citrate, things like that. You can imagine if you have a large number of cations and combine it with an even larger number of anions, at the end of the day you turn out to have a huge number of combinations. So in reality it's for sure millions. In theory it was calculated once, if you talk about ternary mixtures, to be 10 to the power of 20 or 18, but so I don't care about this number. It's millions for sure, probably billions of structures. Whereas if you go to normal solvents in organic chemistry used in the industry, we are talking probably for about 1,000 different structures, not millions. So you have many different structures, and it's very important to mention, if you would like to change the properties of those liquids, you actually do not have to make covalent chemistry. You make ion exchange. Yeah? So in optimizing an ionic liquid, sometimes one functionality is incorporated in the anion and another functionality is coming from the cation, and you can vary the fine-tuning just by making ion exchange reactions. And that's what CBILS actually does, what we will see. History of ionic liquids, again, I don't know if you would like to get this talk as a PDF. You could put it somewhere on your homepage and everybody can read it afterwards in detail, because we don't have too much time to go into detail. But actually ionic liquids are not so young. Yeah? The first ionic liquid, to my knowledge, was described in a patent in 1888 by Gabriel and Weiner, and they called it a liquid gunpowder. So it was ethyl ammonium nitrate. It was not a room temperature ionic liquid, but definitely it was an ionic liquid. The first room temperature ionic liquid was was observed by Paul Walden in 1914 at the University of Rostock. So I made my PhD in Rostock. So 2014, it was 100 years that this ionic liquid was found. But Peter Walden did not really know what it means. First he thought his ethyl ammonium nitrate is not pure because he couldn't get it solid. Yeah? So he purified and purified and purified, but it never got solid. At the end, it turned out that's an ionic liquid, but he didn't call it an ionic liquid. So the term ionic liquid was given by John Bockris in 1955, but it stayed to be a curiosity at that time. So the US Air Force research was searching for new electrolytes for thermal batteries based on eutectic mixtures, and they found the chloroaluminate-based ionic liquids, which were very interesting substances, but again, they were not air stable, they were not water stable. At that time, you had something like 2 or 3 patents a year. Yeah? Nowadays, it's almost 2,000 patents, new patent applications a year. The breakthrough was in 1992, when the first water and air stable ionic liquids has been invented by Sawarodko, again at US Air Force. And the first industrial process using ionic liquid was in 1996, though BASF claimed the Basel process to be the first, but at that time, this one was confidential. So Basel process stands for biphasic acid scavenging utilizing ionic liquids. That's a very nice way how to catch acid in industrial processes. The first engineering application I was involved is the so-called Linde ion compressor. And nowadays we have 29 pilots and 28 commercialized products with ionic liquids. I'm going to show you some details about this. I think it's also important to show you how the field developed in terms of number of publications and number of patents over the years. So that's a non-cumulative graph. If we look here, I skipped the other ones, to the dark blue graph. This is ionic liquids patents, non-cumulative. It started around 2002, and nowadays the last number of 2018, I should have corrected that, is something like 2000, with a compound annual growth rate of 21% over the last 15 years. That's a lot. Patents are an indicator for the transfer of scientific results to a real life world. Yeah? So patents are also used by stock analysts or by brokers. It's not a proof that something is on the right way, but it's a good indication if there are lots of patents. Patents cost a lot of money, so people don't patent something because they have too much money. So if there are lots of patents in many diverse fields, then this means that something is going on in the application. If you compare the same story for nanoparticles, by the way, you see that's the dashed line that we have nowadays, something like 15 or 14,000 patents, new patents every year, with a compound annual growth rate of 16%. But anyway, it's a lot, yeah? And it's also something like 9,000 new publications each year in the field of ionic liquids. So it's not anymore within a very special field of some crazy scientists working with ionic liquids. It has a broad scope of different applications. Let's go to proionic now. We will come to the properties of ionic liquids soon. Proionic was ranked to be among the 5 largest companies in producing ionic liquids in the world by a Frost & Sullivan survey in 2016. So this was something we were, of course, very proud of. Frost & Sullivan is very well known, and actually still proionic, the production of ionic liquids in the world is still pretty small compared to large industries. So we are talking about several hundred tons, maybe 1,000 tons a year. Ionic liquids are pretty expensive still, yeah, expensive. And there are some companies producing ionic liquids. There has been large companies producing, like BASF or Merck or Ionic, but for them, the field was not growing fast enough. So they were heading towards 10,000 tons, 100,000 tons. Yeah? For them, it's just too small. So they stepped out of the field, and there were companies like Proionic left producing these ionic liquids. And so now we are among the top companies producing it. So actually, the company was founded in 2004. Meanwhile, I think we are number 3 in terms of volume worldwide, but it's not so important for me if we are number 5 or number 3. We have a patented production route, which is called the Siebels route, which is absolutely proprietary. We have an industrial ionic liquid production pilot. We also have process engineers specialized in ionic liquids, because it was my strategy, if you would like to introduce new technologies and you are developing new operating fluids, for example, with completely different properties compared to the state of the art, you also have to develop the process, or at least adapt the process to run it, to be successful. So we offer our customers both. We offer the development of the ionic liquid and the process of the ionic liquid, which is very important. Think about recycling ionic liquids in a process which cycles, and you need to have a high recycling rate. If you are not specialized in ionic liquids, you will not be successful. So we have something like 100 active patents or patent applications running right now, which is a lot. We never planned to have so many, but it turned out that we had to patent a lot for all, of course, our synthetic route, which is the heart of the company, is patented. And we also are in the Frontrunner program. If you know this Frontrunner program of FFG, it's for hidden champions, so companies which have something valuable, which have the chance to get world class. Yeah? So they invest money to make companies big, let's say, which are hidden champions. And it's not easy to get into this program, and we were successful. So that's me. I'm working 20 years in applied ionic liquids, and since 2016, I'm also an advisor at Lawrence Berkeley National Lab, Joint Bioenergy Institute, and that's my partner Michael Concha, which founded a whole engineering group, which is the VTU group, with more than 500 people, which is one of the main shareholders of proionic. So he is the boss of the large company, but also the CEO of proionic. So he is really committed. He's a very important investor, and people are very important, as we will see later in building up a company. He's one of those key persons. These are some references. We are in the automotive industry, we are in the chemical industry, we are in the biomass industry, in the electronic industry, and yeah, those are the ones I'm allowed to show you. The production capacity used to be something like 50 tons in 2015. We develop now towards 200 tons per year and go to higher qualities, which is what we call electronic grade. Electronic grade ionic liquids are really hard to make. They have to be produced according to GMP, so good manufacturing practice standards, which is not easy. But they are very valuable, and they have still a large margin. So even if you produce small quantities, you can make a lot of turnover with those kinds of materials. So even in the ton scale, we are still talking about several hundred euros a kilogram for these electrolytes. And we are heading now towards more than 2,000 tons per year in the next years. So we have to build up a new factory, small factory, probably a second in the United States. We will see. What about the price of ionic liquids? So it's like with everything, it's a question of the scale, of course, of the economies of scale. If you would manufacture, so those are two typical ionic liquids, a cheaper one and a more expensive one. So this stands for ethyl methyl imidazolium tetrafluoroboroid and acetate. If you would manufacture it in a kilogram scale, a kilogram, so more or less handcrafted, a kilogram would be something like 350 to 700 euros. Yeah? If you go to the ton scale, this price drops, of course, down to lower price range. And what we are heading to is going to 500 tons. Then you get to completely different numbers. Anyway, 35 euros or 60 euros a kilogram in the 500 ton range is still an expensive material. So if you apply ionic liquids, you have to be clear about that compared to the state of the art, your improvement has to be an order of magnitude at least. Yeah? So it's not worth doing something which is just incrementally better. It must be something completely new. It should be, ideally, it's something disruptive, yeah? Which could not be done before without ionic liquids. So at the end, the total cost of ownership, of course, is important. Sometimes the liquid is expensive, but the cost to operate something goes down dramatically. At the end of the day, it's cheap again. So there are many ways how to think about that. So the next few pictures are not really, let's say, are almost private. Yeah, I just want to show you how it all started. So it started very simple in a garage, more or less a garage laboratory, where actually when it was raining outside, when there was a thunderstorm, I had to protect my equipment from water coming into the lab. It's incredible, but it was like that. But actually, I think it started earlier. It started way earlier, before 2004. It started with a chemistry box of my brothers. In 1974, I have two older brothers. They received a chemistry box at Christmas Eve. And after a few months, they didn't want to play anymore with this chemistry box, so I grabbed it. And I did it without telling somebody, so I did it secret. Yeah? So luckily nothing happened. But this is where I fell in love with chemistry. And it never left me again. The second thing what was very important was during my high school, I had a high school teacher which was really training me. He was the one who was pushing me. It was Thomas Gabriel. And he said to me, you can do it. You can study it. You are clever enough to do it. I personally would never ever thought about it to study chemistry because people studying chemistry were gods to me. Yeah? So I never dared to study chemistry. But he said, you can do it. And he was a motivator, pushing me forward and starting to study chemistry. So I think those two things were important for the future. And actually, I never planned to found a company. Some people want to found a company, but they don't know in which field. So in my case, it was completely the opposite side. It just happened to me. Yeah? So I worked already with ionic liquids, and I always thought about how could I synthesize these liquids easier, cleaner, cheaper. And I had an idea what type of intermediate I would like to use, but I didn't know how to get there. Yeah? And one day in summer vacation in a beach in Greece, in Crete, I had an idea. So this was the inspiration. At that moment I thought, it's just an idea, it's garbage, it's not gonna work. Back in the lab, this was actually the very first experiment. I took a picture thinking about, you were gonna delete it. But I thought, okay, maybe, who knows, yeah? So I took this picture. That's really a ridiculous setup, isn't it? It's just a simple round bottom flask, and I'm just cooking something under reflux. That's all. That's not fancy at all, yeah. But it was the starting point. This was the first experiment. This actually took place. So I would never underestimate if you have a clever idea. Also here, people working here probably have things which are applicable. So if you're a student, PhD student or postdoc or whatever, or scientist, always think about, could I use this for something? Yeah? And of course, what can I learn from it? That's very important always, but could I use it for something? And sometimes it must not be very fancy. It can be very simple. And this is what you see here. That's the real actual first experiment. Followed, and the first experiment was already a little bit successful. That was important. Followed by hundreds more, and then by a patent application late 2003 and the foundation of Proionic 2004. This was our first lab, also not very fancy. Our first employee, Christian. Our first product sold. You see, I was looking younger. This was the first product sold to a customer. A person, so our customer paid several thousand euros for this bottle. Incredible. The first product, I was proud, yeah? The first bulk product. And after that, in 2006, we could license our technology to BASF. That's a particular story. Why? Because we patented it. Probably we can talk about that later in questioning and answer. This was very important to be able to negotiate with a company as big as BASF. So in reality, BASF bought a license from a 3-person garage startup in Leoben, Austria, because they needed highly coordinating ionic liquids. And the best way to synthesize them was our Sibyl's way. That's why they bought it. And they scaled it up to 10 tons until 2008. And this is a picture of a sample from our first small-scale production. And this is a picture after it has been scaled up at BASF. And of course, you can imagine that this one is purer than this one. But for all, it worked in the large scale. That was important for us. So this was the first innovation. because it's implemented. It's running on large scale. Today, Proionic looks more like this. We are not a big company. We have something like 18 headcounts, 15 full, wie sagt man? Yeah, full-time equivalent. Thank you very much. So, for example, what you see here is electronic-grade ionic liquid in stainless steel kegs with argon under argon. They are very, very expensive, by the way. So this is 1,500 liter of real expensive stuff, and this is used for biomass applications. So, what is the civils process? I'm not going into detail as well. Only prominent example of the dialkylimidazolium based ionic liquids. So if you would make a dialkylimidazolium ionic liquid, let's say that's ethyl methylimidazolium acetate, you would start conventionally with methylimidazole and alkylate it using ethyl chloride. So ethyl chloride is not very nice. It's suspicious to be cancerogenic. It harms the atmosphere. You alkylate it that way, you end up with an intermediate with a chloride anion, and then you have to exchange the chloride anion against the acetate anion. So what you produce is 1 molar equivalent of waste, at least. You cannot prevent it. You use toxic chemicals, carcinogenic chemicals, and you have traces of chloride in your final product, at least in 1,000 ppm range, which is corrosive to metals if you run it in real application. So what we do is a completely different way. Let's skip the first step. We alkylate using dialkyl esters of carbonic acid at relatively high temperature with the right catalyst. Our intermediate is now the same cation, but it's an alkyl carbonate, for example, a methyl carbonate. And if you would like to make now an acetate out of a methyl carbonate, the only thing you have to do is you have to throw 1 molar equivalent of acetic acid onto it. It hydrolyzes, you get methanol and CO2. CO2 goes out, the equilibrium is shifted to the right side until 100% conversion, always, no matter which equilibrium you have. This also works with ammonium salts, for example, if you have no acid. The acid has to be at least has to have a pKa of smaller than 9, but that's pretty weak. It almost every time works. And the CO2 formed together with the methanol can be recycled back to the starting alkylating agent. So it's free of chloride, it's free of carcinogenic materials, and in theory it's free of waste, and you always have 100% conversion. So I would say that's the reason why Proionic still exists, because we have this process which is completely different to any other process in the world. And it has proven that it works in large scale. It has proven that it works for very high quality ionic liquids to do it that way. It works with a lot of substrates. I'm going quickly over this slide, but it does not only work with imidazolium. It works with many substrates. It does not work with those, not with sulfonium, pyridinium, or pyrrolium, but those are not so important. Where are we working in which fields? Also quick. I could spend an hour on this slide, but I will not. We manufacture ionic liquids, high-tech lubricants for high-pressure gas compression. We are in hydraulic fluids and sealing liquids in high-temperature cooling. That's something I will gonna show you. Electrolytes, biomass conversion in industrial ceramics, in unflammable hydraulic fluids. We can weld aramide fibers like Kevlar. That's also a patent. Kevlar could not be welded so far. It works with meta-aramide, para-aramide copolymer. So we can actually make a connection substance in substance between Kevlar fibers. That's interesting for airplanes, for example. Yeah? And it's very interesting. Kevlar is almost insoluble in anything, but there are thousands of ionic liquids which can be used in order to do that. We are in hydrogen storage and in microwave adhesives, which means adhesives which absorb microwave by ionic liquids. So you can heat them up and cure them by applying microwave. So you heat up not the whole bodies you want to adhese. You only heat up the glue in a few seconds. And that's where we're working on. Properties of ionic liquids. I might too quick. No, you can still follow me? Good. There are many pictures. There are many slides. I have to be quick. So this is an old picture. It has been made even before the proionic time, but I always show it. It shows butyl methyl imidazolium tetrafluoroborohydride. That's a substance with around 220 molecular weight. It's not so much. At a temperature of 171 degrees centigrade, because I could have heated it up to 300 and more, but the plate was not good enough. The performance of the plate was not enough. At 1 microbar pressure, what do you see? It's not boiling. A substance with this molecular weight at this temperature and at this pressure should boil. It's not boiling. Why? So I already said millions of structures. Ionic liquids, except some very rare cases, do not have, or let's say they have no measurable, almost immeasurable vapor pressure. So to be precise, I was about to say do not have a vapor pressure. That's not precise. Yeah? Vapor pressure is in the range not so far away from a typical solid. It's difficult to measure the vapor pressure of an ionic liquid. It's something like 10 to the minus 15 millibar or lower. So you can, in reality, you can forget about it. NASA uses ionic liquids for lubrication under space conditions. Nothing happens. So we have an extremely low vapor pressure. This means also we have no boiling point, and we are virtually inflammable, because to form a flame, you need a gas phase. Virtually means if you heat it up above the decomposition temperature, decomposition products could be flammable. But it's a completely different story. If you put away your heat source, it's not burning. Yeah? You can, some of them are totally inflammable. Some of them are only burning as long as there is any kind of heat coming into the liquid. That's completely different to a compound like gasoline. Gasoline has a high decomposition point, but it burns immediately because it has a vapor phase. So for some people working with optics, maybe that's probably interesting. Pretty high refractive indices, also pretty high densities. Excellent thermal stability. If I talk about that, I mean long-term thermal stability under application conditions. I'm not talking about thermal gravimetric analysis with a quick heating rate. I'm talking about months or years. We have ionic liquids with 300 degrees centigrade and more, or working for years. Yeah? We have very unusual solvation properties. There are ionic liquids which are able to make extremely strong hydrogen bonds. Some of them make even a completely different chemistry. I have no time to explain that now, but there are some papers who made it into angewandte chemistry coming from proionic and in cooperation with Robin Rogers, where we showed that we have a new type of chemistry because of these hydrogen bonds. This also opens up the possibility to dissolve biomass. And if I say dissolve, I'm not meaning decompose and bring into liquid phase. I mean keeping the biomass entirely intact. Especially the biopolymers are not broken. You can use this for many different applications. I will give you some examples later. I'll show you one funny example right now. What you see here is the dissolution of medical hemp. So we are talking about medical cannabis. So why are we doing that? Cannabis contains a lot of valuable pharmaceutical active compounds. And there is more and more interest in the world using those compounds. I'm not talking about THC or cannabidiol, CBD. There are hundreds of other compounds in cannabis, but it's hard to get them out normally. You have to dry it, you have to grind it, you have to extract it. On the way, in these steps, you lose a lot of your compounds. They are decomposed mechanically, thermally. Using an ionic liquid, you can just dissolve this, and once it is in solution, you can do whatever you want. You have diverse ways to get it out. Not forget about the ionic liquid has no vapor pressure. So every compound which has a vapor pressure is not the ionic liquid. And you can get it out, however you want. If you apply vacuum or heat, you will get it out. You can extract, you can do many things. You can not only dissolve hemp, you can dissolve wood, you can dissolve wool, you can dissolve shrimp shells, what you see later. So you can dissolve almost anything. I have a reef tank at home. Once a fish was jumping out and he was dead. I said, oh, that's really poor. But okay, I tried to dissolve the fish. I know it's funny, but it worked. I could dissolve the whole fish. Yeah? The only thing which was left were parts of the skeleton. So that's really funny. We have extreme low compressibilities. Lower than water. Water is extremely incompressible. Ionic liquids are way more incompressible. That's because of the Coulomb forces. This also goes in the other direction. We can take ionic liquids if they are really pure and degassed and apply a tension of a -1000 bar on it without cavitation. That's impossible with any other liquid. I don't tell you now how you apply and measure this tension. It's not easy, but that's, I don't know if you can hear it because it's not so loud. You see here a movie, I started soon, where an ionic liquid cavitates at around -700 bar. If you wait, again. Did you hear it? Again? It makes click. Yeah? So that's a cavitating ionic liquid. Why does it cavitate? It's not because of the ionic liquid, it's because of traces of moisture inside the ionic liquid. So that's something you can't do with other liquids. Corrosion of ionic liquids falls too short. Inorganic salts are behaving completely different as ionic liquids. If somebody tells you, oh, these are salts, they're all corrosive, it's not true. We even have ionic liquids which are corrosion protective. We have nanostructural segregation. That's something I told you already. This is also interesting in regard of magnetism. What you see here is a magnetic ionic liquid. It's paramagnetic, probably super paramagnetic. And it's attracted by a magnet. We have a patent on extraction with magnetic ionic liquids. So this also works if the density of the two liquids is equal. And so you can apply it without mechanical equipment. I think with what is really important, so good lubrication properties, okay, electrical conductivity, it's an electrolyte, of course. Large electrochemical windows, really large windows. This is one of the most important properties of ionic liquids, up to 6 volts and even more. I will show you later why. Outstanding microwave absorbers, and they are bactericide to bacteriostatic. You have no biofouling. Nothing grows in ionic liquids, not because they are toxic, because of the high osmotic pressure. So that's that easy. Applications. Yeah, I have to speed up. But I like the sentence of Roy Amara. We tend to overestimate the effect of a technology in the short run and underestimate it in the long run. Ionic liquids went through a typical hype cycle. So as you could see, the large numbers of patents and publications, there was a real hype, and then the things didn't work in reality so easy. People said, it's all garbage, it's not going to work at all. Companies dropped out of programs, and now we are on this, we are something like here now, I would say. The whole technology gets more and more mature, and we have to do the real work now. The party is over, yeah? Here has been the party, we have to do the real work now. So typical application fields of ionic liquids are solvents, metal finishing, energetic materials, biotechnology, analytics, pharmaceuticals, food technology, engineering fluids, thermal fluids, chemical reactions and reagents, separation processes, electrochemical cell, and devices. And I personally think those, oh, you almost can't see it here. Here you can see it, I hope you see it. Those are the ones which have a chance to get into the mass markets. because of several reasons. That's my personal opinion. I skip this. I also don't want to go into this list into detail. I recently wrote a chapter towards industrialization of ionic liquids for a book, which is Commercial Applications of Ionic Liquids by Mark B. Shiflett. That's a professor in Kansas. Will be published by Springer this year. Yeah? I did a lot of research to find out these ionic liquid applications, but I thought it's worth doing it. It took me really months of work. Always, I was continuously doing, hundreds of emails and phone calls and things like that. I just wanted to show there are ionic liquid applications in the world. And if you are looking on the role the ionic liquid plays, it's a lot electrolytes, it's a lot operating fluids, performance additives, solvents. Yeah, that's important. If you're interested, you can read in detail if I send you the paper. The PDF. So let's go to examples, applications of ionic liquids. So I'm going into a special field of proionic, which is operating ionic liquids in the metallurgical industry as cooling agents. First step, which was done at the University of Rostock, what happens if you apply a hot part, a hot metal, into an ionic liquid? In this case, it's an aluminum cylinder at 540 degrees centigrade. What you see now is 1,000 milliseconds. It's a slow motion. And the first part of the movie shows water, and the second part shows an ionic liquid. So what you see in water, the picture looks like that. You get film boiling. The water, Leidenfrost effect, immediately evaporates. You get a film of steam on the outer side of the cylinder. And actually, there's not much contact to the cylinder. Though water has a high heat capacity and a high heat of evaporation, in reality, cooling down is not so quick in the first seconds, and it's not equal distributed. The cooling is not equally distributed, so you get thermal tension in a metal. What happens if you do the same thing with an ionic liquid, which has no vapor pressure? That was an interesting question. We speed up. No. Okay. That's an ionic liquid now. You see a completely different picture. You see almost no gas bubbles. The structures you see here are differences in refractive index because of the heat. There are only a few gas bubbles, and it's all extremely turbulent. Though the ionic liquid has only something like 60% heat capacity, the cooling is way quicker at the end of the day, and it's equally distributed. So that was 500 degrees centigrade. Now we go to something different. I show you 3 quick movies. The first one shows what happens if you throw a bottle of water into molten steel on the surface. So water is the state-of-the-art coolant. That's a Coke bottle. I'm not making advertisement here. So this was the surface. Pretty explosive. As you can imagine, you form hydrogen, you form water vapor. So don't do it in your...
How would you do that?
Right. So the next picture is a real accident. If the same thing happens beneath the surface, the whole story looks a little bit more difficult. So you see, that's serious. That's really serious. So we found out there are some ionic liquids which actually are thermally very stable. But even in the case they get in direct contact to a molten metal, they almost do nothing. And this has been proven so this was many different projects until we made this movie. What you see here is the introduction of some 500 milliliters of ionic liquids per second into 250 tons of molten copper. That has been taken in Tyrol. And of course, this was not the first experiment, of course. This is the first generation of ionic liquids where we did it. Meanwhile, we have number 3, which are even less reactive than the first generation. I don't know why. I don't see the, how do you call it, the Balken. But so, okay. What you see, he's introducing the ionic liquid already. You see there is some movement, but that's all. There is no explosion. Meanwhile, this is applied under industrial conditions for more than 2.5 years now. The ionic liquid is even too stable, so it hasn't changed. So it's used at several sites in the industry. There was also already one accident, and it proved to be safe. And if you have such a cooling liquid, you can completely change the geometry of such devices. Because using the state-of-the-art cooling agent water, it was forbidden to cool, for example, beneath the level of the molten metal. Now you can do that. Or think about parts like a gas nozzle. There are gas nozzles which are very expensive, and the end of the lifetime is breaking of the gas nozzle. So you couldn't cool it, because breaking would have meant that it comes into contact with water. Now you can cool it, and it means that it has a life cycle. The life cycle is increased already by more than 10 times. And that's only possible with such a liquid. We come to another field of application, which is storing hydrogen in ionic liquids. Based on a theoretical concept, I found out that the stability of borohydrides increases in this direction. There is some reason why, no time to explain it now. The stability means the thermal stability and also the hydrolytic stability. On this graph, you see here sodium borohydride solution, and you see diverse ionic liquids stored for more than 2 years. They are ready formulated solutions with the water inside, which has been used for the hydrolytic release of the hydrogen later. But these formulations are completely stable, whereas the sodium borohydride formulation is not stable at all. And this has been used already by Daimler Chrysler in the 90s for a car which was called natrium, yeah? Not sodium, it's funny, they call it natrium. And it used hydrogen in this form, but it was not stable enough. Using ionic liquids, it turns out that this is very stable. And I'm also not going into this detail, but that's something like it works. So you have skipped this side, you have the borohydride, you bring it together with water and the catalyst in contact, you release the hydrogen, you get a metaborate. The metaborate makes a liquid ion exchange reaction, which is patented with sodium borohydride, and it's recycled, and the formed sodium metaborate is the starting material to produce sodium borohydride. So those are closed circles. It's still too expensive, but it works. We also have developed catalysts which are not based on noble metals, and it's safe, and it's a nice way how to store hydrogen. This movie shows you have this ionic liquid here, which 5% hydrogen inside at 23.7 degrees centigrade. I'm telling the temperature because there are other liquid hydrogen storing materials which work at the 150 to 200 degrees centigrade. So this works at room temperature. This is a catalyst. You see 5 weight % is pretty much. It's not flammable, though it contains hydrogen. So if you apply the catalyst, immediately the hydrogen is released. Yeah? So this has been developed up to a demonstrator level, 4 projects in a line. We already have demonstrators showing it in combination with fuel cells that you can really use it. And it has also been developed for automotive. And for this reason, I would like to show you something else. First of all, I would like to show you how dangerous hydrogen is. You see the explosion of 100 liters of hydrogen air mixture. For all you hear it, that's in a balloon, yeah? 100 liters, only 100. So it's really dangerous. In the next movie, that's something which has been done at ICT Fraunhofer in Karlsruhe. That's a so-called Gunfire test. That's something you have to pass if you would like to develop a storage for automotive. So it mimics a high velocity impact between two cars. So what you do, you shoot under standardized conditions, not by a person, by a machine, onto your tank. There are 3 levels of increasing let's say the conditions. The highest level is shooting with propane flames around and using an ammunition which has a tracer in the background, so a burning ammunition. And so we have here now, what you will see is 2,200 liters of hydrogen equivalent. Think about the 100 liters before. This is 2,200 liters of hydrogen equivalent. First movie is under normal speed. No. This one. So you see the tank. This is the propane flame around in order to ignite any hydrogen which is formed. And boom. You see nothing happens. If you do the same with regular hydrogen tanks, only a few, really a very few, pass this test. The same thing under high speed. You will see the burning bullet coming from the right side, passing through the tank. The tank forms an aerosol. This was the part I was most anxious about, or I feared most, because I was fearing that the aerosol, because it's an organic liquid, might be ignited by the flames, not because of the hydrogen, because of the fact that it's organic. This was not the case. So Fraunhofer stated that was the safest liquid hydrogen storage they've ever seen so far. Now we are looking for money to further develop the whole story, and we need several millions now in the next step. So that's something. Hydrogen, I have the feeling hydrogen is still a topic which now gets more and more attractive again in the last month or in the last year maybe. So
how economic is it to store hydrogen in a liquid with, let's say, 5% ratio?
How?
Economic, yeah.
Economically, it's like that. If you calculate the price per kilogram hydrogen, it should be for automotive around $5, $6, $7, something like that. And it actually is around 60 in the moment. Yeah? Most of it has to do with economy of scale of sodium borohydride. This is produced at 1,000 tons only. It's a fine chemical. It's not a bulk chemical on the large scale. But we have some ideas how we can make the recycling way cheaper, but that's why we need money. I might use some 5 minutes too much. I hope this is okay for you, because there will be some thrilling things coming up.
Very interesting.
So you have to leave?
I have a meeting, sorry.
So you can see the YouTube.
Thank
Probably.
you.
Okay. Is that okay for you? Okay. Nobody says no. Good. So the next thing is the so-called Ionic compressor of Linde. That's something which has been invented by me and by one other person on the ionic liquid side and 2 other persons on the mechanical side of Linde. That's a compressor which uses liquid pistons. So that's a reality. This compressor exists. It is, as far as I know, it has a market share in Japan which is above 80%, because it's extremely simple. So instead of using a conventional compressor to compress hydrogen to fuel cell cars, yeah, we talk about 1,000 bar of hydrogen, which is really a lot. Not easy to compress such a small gas to 1,000 bar. The normal compressor has something like 500, conventional compressor, 500 moving parts. The ionic liquid compressor of the first generation had only 8 moving parts. We substituted everything from the mechanic by ionic liquid hydraulics. So we have no problems with sealing, with wear, with contamination. Life cycle was going up to way more than 10,000 hours. Nowadays, the design has changed a little bit. Nowadays, it's a 5-step compression. There is a short movie from Linde.
The compressor station are the ionic compressor, together with the downstream separators, as well as the high-pressure storage tanks, and finally the cooling unit. All the modules are housed in a 14-foot container. So how does the ionic compressor actually work? For hydrogen fueling stations, Linde has developed a 5-stage ionic compressor. The pistons of the machine move up and down hydraulically. On the top of the pistons, there is the ionic liquid, which is compressed through the compressor cylinder as a liquid piston, together with the hydrogen. At the end of the compression process, the ionic liquid is separated from the hydrogen by the separators and returned to circulation. This design results in less wear and tear, as well as much higher energy efficiency, thanks to optimized cooling and avoidance of parasitic volume during the compression process. Compared to a conventional piston compressor, energy savings are around 40%.
So 40% energy savings is a lot. And that's because of the ionic liquid has the following properties: almost incompressible. That's what you need at that high pressure. No vapor pressure, so it will not contaminate the hydrogen. And a low solubility of the hydrogen, very low solubility in the ionic liquid. So that's a very nice commercialized product. And I also want to mention the dye-sensitized solar cell, which is an organic solar cell based on diverse dyes and ionic liquid as the electrolyte. This is a translucent solar cell, which was invented by Michael Grätzl, Professor Michael Grätzl of the Swiss Federal Institute of Technology in Lausanne, which was almost nominated for the Nobel Prize. So he was at the, what's Dreiervorschlag of English?
Shortlist.
Shortlist, yeah. But he didn't make it. Dye-sensitized solar cells are on the way to get implemented more and more. There is an example in Graz, which is the Science Tower. So this is all dye-sensitized solar cells. There are other examples, like here in Lausanne. You can imagine if you have a translucent solar cell, you can mount it on a facade of buildings, and especially large cities like New York City, for example. They have not much space on the roof, on the top of buildings, but they have a lot of space on the facade of the buildings, and that would be an interesting application. Here also the ionic liquid plays an important role because, again, it has no vapor pressure, and that's a structure with a lot of surface which gets very hot every day and gets cold in the night. And so in terms of, let's say, mechanical stress and in terms of safety, unflammability, and performance, that's very important. Another application, we are on the way to the last slides, is a new type of ultra capacitor. This is a company we work together, which is called SEPGO. They call that technology a C-ion cell. It is nano carbon with special ionic liquids. If you think about the energy stored is 1/2 the capacity times the voltage squared. So if you have a high capacity coming from the nanocarbon, that's good. But if you have a large electrochemical window, this is even better because it's squared, of course. Yeah. So altogether, this results in super caps, which are right now, they have already passed this. This generation 3 is already on the market. The generation 4, which is under development right now, has a performance which is comparable to lithium ion batteries. But for all, the charging time is in the range of 1 to 5 minutes. Yeah? Sometimes even only 30 seconds in reality. So if you have these tools, for example, you charge them up in seconds. They have, for example, cellular phones, of course, Also transport. This is an airport car which charges up in something like 35 seconds. And that's really interesting. And on top of that, what is also important is the safety, because lithium-ion batteries are not really, let's say, harmless. Yeah, I show you a small movie. What happens? Yeah, all my movies have to do with fire and explosions. I'm sorry. So that's a battery abuse test done by an external institute. Company is in Oxford, where they penetrate a lithium-ion cell and a septal cell. And that's what you see in a few seconds. And this is not fake, that's reality. That's what the lithium-ion cell does if you penetrate it. You can do, if you have an old cellular phone, be careful, take a nail and a hammer, and you will see the same thing. So when I saw the movie first time, I didn't believe it, but it's true. The ultracap, let's say, or C-ion cell, is still working after this penetration test, by the way. There's no safety concern. Think about sitting in an airplane with several hundred of those lithium-ion battery cells in terms of safety. But okay, so we are coming to the last field of applications, which is biomass, and that's something I like very much. This is a company called Natural Fiber Welding, and I have these slides with permission from them, one of our customers. What are they doing? They are welding natural fibers. What for? So what you see here is a microscopic picture of fibers which has been stained with fluorescent stains under a confocal microscope, and you see those silk fibers before the welding and after the welding. The ionic liquid literally swells the biopolymers, which diffuse into each other, and after that, so by breaking of the hydrogen bonds, yeah, and after that you apply an anti-solvent like water, hydrogen bonds are reformed, you dry it, and then you get this welded fiber. So what can you do with a natural fiber which is welded? So this is, if this is the world's consumption of synthetic fibers, then this is the world consumption of natural fibers like cotton, wool, silk, linen. Yeah. What you see here, this circle is the cellulose production of nature. Cellulose is the most abundant biopolymer in a year, and this is 1% of it. And this is the produced available waste cotton in the world. So that's the cotton we throw away. Why do we throw it away? Because we can't recycle it. Cotton consists out of filaments which have a certain length. And the yarn made from these filaments only has its strength because of friction between the filaments. And the shorter the filaments get, the lower the friction is, and the lower the resistance of the yarn gets. So if you are able to weld the fibers, the filaments, to each other, it's not friction anymore which keeps them together. It's a chemical bond. Sorry, not really. It's a hydrogen bond. Almost a chemical bond, let's say. But it works. And if you do this, you see the following things. Normal filament polyester is very durable, is quick drying, and very strong. But it's not very comfortable, and it's not odor resistant. You know it's quickly, you smell if you wear polyester. Cotton, normal cotton, is very comfortable, very sustainable, and odor resistant, but not very durable, not very strong, and not quick drying. If you weld cotton, you get the performance, you get the best of both. You get the properties of both. So this is already implemented, so they are already producing it. This means your clothes don't produce, if you would make garments with this material, you don't produce microplastic anymore. It's decomposable. You can utilize the clothing longer. There are way more resistance against wear and shear forces. So your clothing are just, they last longer until they are gone. you can recycle them. You can really literally take, for example, denim, yeah, or use denim, disintegrate the fibers mechanically, make a new yarn and weld the fibers together, and you have something which is almost of the same quality of the starting yarn. And so this is really something which has a potential to go in a mass market. We are talking about hundreds of millions of euros per year in this market, and where natural fiber welding is leading, and it's based on ionic liquids. And it looks like this, for example. That's a recycled welded textile, which looks really nice. And even more, you can even make tables out of used denim. So that's not a print. That's a real table. This material has, let's say, the thickness like a centimeter, and it's hard as wood. So it's welded, it's not glued, there is no adhesive, it's only denim. Yeah? So you can make fancy things out of it. I really like this, to be honest. It's something, I think it's fantastic. So, the very last slides, you can do a similar thing. Sorry for taking so long. You can do a similar thing with shrimp shells. A company, Marisignum, which is another customer, is dissolving shrimp shells, purifying them, and then spinning fibers or making films out of the chitin. And chitin is a very interesting material. It's the second most abundant biopolymer on the planet. It's of course biodegradable again, but it has completely different properties compared to cellulose. And so they are right now scaling up. The pilot is running. They're already in the low ton scale, and they say they are going to unlock the chitin economy, because you can make products for agriculture, plastics which are biodegradable, for filtration, textiles, for medical applications. So you have a new type of wound tissue which is close enough to human skin that human cells grow on the surface of the tissue. That's very interesting. Animal feed, packaging, cosmetics. That's also something which only works with ionic liquids. They got the highest molecular weight chitin ever produced in the world. That's also under the no, I lost the word, sorry. Robin Rogers, which is a very well-known person in the field of ionic liquids, is also one of the people who started this, the whole field was of chitin. So the last picture, it even goes into medical. Just recently we had a publication it's not implemented yet, but they took a huge step towards a pill delivering insulin instead of injection of insulin. Yeah? This is done at the Wyss Institute at Harvard. This work has been done at the Wyss Institute of Harvard, and it works already on a mouse model. And the insulin is something like packaged in an ionic liquid, and it survives the stomach. It passes through the stomach, and later the capsule is dissolved, and the insulin is active, and it's incorporated into the body. That's another application of ionic liquids, is drug delivery. That's just an example. There are other examples, because ionic liquids also stabilize many compounds to a high degree by hydrogen bond interaction. That's also true for enzymes, for example. Some enzymes survive 100 or 1,000 times longer than they normally would do. Storing of enzymes, applying them in diverse applications, also for biomass digestion, for example. So there is also, by the way, some reasons why we think that enzymes are stabilized. But that's something from last year, end of last year, and I really love this story, of course, because that's really another example that there are many options to apply ionic liquids. So, coming to the end of my talk, how does it feel to found a company and build it up? I would say pictures are more than words. First, it feels a little bit like that. So let's do it. Let's go up the rocks and do it. After a certain time, of course, because that's, as you can see, is free climbing, you realize it's gonna be a little bit too dangerous, and it gets steeper. So you need some ropes, you need some safety, yeah? Which means you need good partners in order to build up your company. Sometimes it looks pretty much like this. I heard that somebody giving a twist talk called it feels like a roller coaster, a coaster, yeah. I think that's a good description, but I used to climb when I was younger, and I also think that's a good description. Sometimes it's really foggy. You don't know where you're going to, and it's dangerous, and you can fall down somewhere. But it's all about the team. You are working together. You have a strong team working together, and that finally, if you are making it to the top, it's just absolutely fantastic. And when I say top, I mean there are many tops. I'm not saying I'm making it to the top in the field of ionic liquids. I made it to my private top. Yeah? So I started from a very, very easy experiment, and I am now in the ton scale and worldwide acknowledged. So it feels like this. What does it need to drive a company? For all, passion, people, and of course profit. And I would say in this order. So thank you very much for your attention, and sorry for taking 15 minutes too long.